Hi, this is the notes for Chapter 6. These are the second set of notes that you'll take in this chapter about Riemann sums, named for Bernhard Riemann, who's a very important German mathematician toward the middle end of the 19th century, who did a lot of the work sort of shoring up the foundations of calculus and that sort of thing. He was a very prolific mathematician, did a lot of cool stuff. And this is, of all the things that could be named for him, he'd probably roll over in his grave about this one because it's pretty mundane. But let me show you. I'll start off with an example here. In the last set of notes, we talked about how to find area when you can use some knowledge that you have from geometry, like areas of triangles or circles or trapezoids, things like that we know about. But what if the function that you want to find the area of isn't one of those nice geometric sort of shapes? Then what to do? So then we approximate the area, and there's different ways of doing that. The most simple way of doing that is to do it with rectangles. So we could divide this up into some rectangles. I'm going to make it, they don't have to be, they often for us, they'll all have the same width, all of our rectangles, but they don't have to. And just to emphasize that point, I'll divide this up into 4 what we call sub-intervals, right? And then you pick a point in here. It doesn't have to be this one or this one, so I'll pick some point, let's say here, in this, and I'll pick a point here. I'll make that the height of this rectangle, and I'll pick a point here, and I'll make that the height of this rectangle, and then I'll pick a point here, and I'll make that the height here. So this, if we add up the heights of these 4 rectangles, we have an approximation. Maybe it's not a great one, but we have an approximation for the area here. So the area from A to B, we'll call this our f of x function. Under the f of x function, don't forget your dx, is approximately equal to the sum of the areas of those rectangles. Approximately, right? And note that, this is a very important note, that what would happen if you let the number of rectangles between A and B approach infinity? Or, in other words, if you let the limit of delta x, where delta x here we mean we'll let this be the largest width of any rectangle. So here our delta x would be this one, right? So let delta x just be the largest width of any of the rectangles. If we let that largest width approach 0, if we force the largest width to approach 0, that's going to force the number of rectangles to go to infinity, right? So the limit of the sum of all the rectangles, the areas. Now, how could we represent those areas? Well, each one of these areas is the value of a function at some special x value. And I think our book puts a little asterisk next to there, or maybe they put, I can't remember what they do there. But it's a special x value that's in the interval, whichever interval we're talking about, and then times delta x, which is how wide, right? So we do that for each rectangle. So the limit as delta x approaches infinity, where delta x is the biggest rectangle, and this is the area of a rectangle. This is how high the rectangle is, and this is how wide it is, right? And this is like the ith interval. Sometimes you see we could put things here and try to have a way of saying that it's going all the way through all the rectangles, however many of them there are. But point is that if you let the limit of the biggest rectangle, the width of the biggest one, go to 0, and you add up all those, that limit will approach the actual area, because you'll get infinitely many rectangles. So that's actually equal to this. Now, if ever there was an unwieldy expression, that's it. And we're not really going to deal with that expression much, except that sometimes you might see this, and you have to recognize, and I would say to you, the limit of the sum of all these areas, that's the motivation for this symbol. It's like an elongated S. It's like the sum of all of these. And maybe this is the first glimpse that we have to understand why the dx is here. This is like the height and just like we have dy dx, those things are really things that have approached 0. But here, this is like the infinitesimal width. So if you understand that this is really like the sum of all of these areas, these expressions actually look very, very similar. F of x delta x, f of x dx, the sum, and then this is our like fancy calculus. So this means the actual area, and this is how we could define that. And then again, interesting to note that just like in the beginning of calculus, derivatives were defined in terms of limits. So are areas, right? An area is also the limit here of many, many, many rectangles as the rectangles go off to infinity, the number of them, right? Okay, so that's the idea here. This is called this kind of summing of rectangles is called a Riemann sum. So, let me show you what we're actually going to be doing here. So let's say we have f of x equal to x squared. And we're supposed to, let's use a right Riemann sum. I'll tell you what that means in a second. With 4 equal subdivisions, so 4 rectangles, to approximate the area from 1 to 3 under f of x dx. You don't have to put that dot in there. I'm just putting that there to emphasize that this is that area of rectangles. To do this one, I'm going to make a sketch. You don't need to make a sketch to do these problems, I think, but sometimes it helps. So here's one. This would be at the point 1, 1, and then 2, 4, and 3, 9, right? It's part of this parabola like this. And since we're doing 4 equal subdivisions, I think we also probably want to have the point here at 1.5 and at 2.5. Right? Now, to do a right Riemann sum, right means that instead of just sort of randomly picking a point inside this interval, we're going to always pick for our rectangles the very rightmost edge of the subinterval. So in the interval from 1 to 1.5, in that subinterval, I'm going to pick the right-hand edge to be my height. Likewise here, I'm going to pick the right edge. I'm going to pick the right edge, and I'm going to pick the right edge. Now, if you're thinking to yourself, wow, that's a pretty lousy approximation, in this case, you're right. It is a pretty lousy approximation, but it is nonetheless an approximation. And even if we used a right Riemann sum, even with this function, if we let the number of rectangles approach infinity, that would still approach the exact area. The errors would get smaller and smaller and smaller to 0. And I might ask you this question: would a right Riemann sum always overestimate area? And you think about, like, for what kinds of functions would it overestimate and when would it underestimate and that sort of thing. All right, so what are the areas of my rectangles? Well, notice that each one of the rectangles is 0.5 wide, right? Not 1 wide, it's 0.5 wide. So 0.5 times, and then the height of each rectangle is the value of the function at the right endpoint. So that's 0.5 times f of 1.5 plus 0.5 times f of 2 plus 0.5 times f of 2.5 plus 0.5 times f of 3. Right? That's how wide each rectangle is, and we're using the right edge of each interval to plug into the function to figure out how high each rectangle is. And if you notice here that there's a 0.5 in each one of those, you could factor that out if you want to. And then, so f of 1.5 squared is 2.25, 2 squared is 4, 2.5 squared is 6.25, and 3 squared is 9. So whatever this adds up to, that looks like that's 8.5, 12.5, 21.5, 21 and a half, which is 43 over 4. Oh dear. I don't know if that's right or not. Might have to check me there. 21. Yeah, maybe. You can check that. So check that with your calculator and fix that if it's wrong, please. Okay, there you go. So we just found a right Riemann sum. Now, for the same function, find the left Riemann sum. And again, we'll do with 4 equal subdivisions. Oops, I'm off the page there. You can't see that. Equal subdivisions. So I'll just resketch the graph because I don't want to clutter that one up. So I have the same thing, 1, 2, 3, and then there's my 0.5s. So this time I'm going to use the left endpoints of the intervals to make the rectangle. So instead of using this one, I'm going to come, here's my first rectangle, here, here, and here. So this one is going to clearly underestimate, right? And you notice that the setup's really similar. It's 0.5 times f of 1 this time, right? This is 1, 1.5, 2, 2.5, and 3. So now I'm going to use the left. So it's, and the rest of the terms are going to be the same, right? Except we're not going to have that last one. So plus 0.5 times f of 1.5 plus 0.5 times f of 2 plus 0.5 times f of 2.5. There's my 4 rectangles. And now we're using the heights, the left edges, to define the heights of the rectangles. So let's see, f of 1 is just 1, and then I have the same as those 3 values, plus 2.25 plus 4 plus 6.25. So that's, let's see, 8, did I say 9.5 up here? Let's go back and look at this again. So, sorry, it's bugging me. That's 8.5, 12.5, 20. Oh, that's right. That's what we had before. So I don't know. Maybe that's right. This is 8.5 plus 5. That's 13.5, which is 27 halves. So 27 over 4, I think. You can check that again for me, please. That's right. Okay. There's also something called a midpoint rectangle, where instead of using the left or the right edge, you use the midpoint. So here that would have to use 1.25. Let me just write out what it would look like, and you can try it in your calculator if you want. I'm not going to chance that one. Midpoint sum here would have 0.5 times, and then we use the midpoint of each interval. The first interval is from 1 to 1.5, so I'd use f of 1.25 to define that. And you might be thinking to yourself, oh, that'll probably be a better estimate because I'll have like a little bit extra here and a little bit short here, so maybe it'd be closer to the real thing. And you'd be right, it tends to give a better estimate, not always, but usually. And then the second would be in between 1.5 and 2, so that'd be f of 1.75. And then, of course, this is calculator work here, right? 2.25 is midpoint there, and f of 2.75. Right? So this would be the midpoint sum, whatever that is. And I would bet you a large sum of money that that's in between this and this. Okay? And then, last but not least, we also can use a trapezoid approximation. And just for thoroughness, I'm going to use the same example so we can compare what we got. So here's my same function, 1, 1, 2, 4, 3, 9. Sorry, kind of missed the points there. And we'll do 4 of them again. So that's 1.5 and 2.5. But this time we're going to do using 4 trapezoids and of equal subdivisions. So here, instead of making rectangles, we're just going to connect these two, right? Connect, 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 connect. And if you're looking at that and thinking, oh, that's probably better than any of the other ones we've done, you'd be right. This tends to be the best of those of the options. So using 4 trapezoids, first you have to remember, we saw this in the first part, the first notes, remember that the area of a trapezoid is equal to the base of the trapezoid. That's sometimes called height in geometry, but here we're going to think of it as the base over 2 and then times the sum of the heights. For us in calculus, trapezoids are always going to be oriented this way with the base on the axis and then the 2 heights, so this is the way we'll think about that. So let's see if we can set that up. For each trapezoid, we have the base of the trapezoid is 0.5 over 2, and then the sum of this would be f of 1 plus f of 1.5 plus base over 2 times f of 1.5 is f of 2. plus 0.5 is 2 f of, this is the, you notice that some of them get used twice because this height here, it's the right edge of this trapezoid, but it's also the left edge of this trapezoid. That's why that's showing up 2 times. And then the last trapezoid, if I can squeeze it in here on the screen, would be f of 2.5, so f of 3. Right. And doing a little simplifying, you can see there's a 1/4, factors out everywhere. F of 1 is 1. I've got 2 of these, so that's f of 1.5 is 2.25. 2 of those is 4.5. And then I've got 2 of these. F of 2 is 4, so 2 of those is 8. You can just jam this whole thing into your calculator, right? I'm just trying to do it without, because I don't have one handy here. 6.25, I've got 2 of those, so that's 12.5. And then an f of 3 there, and let's see, that's 9, and 9 is 18, and 17 is 35 over 4. And that's pretty squarely in the middle of our other 2 approximations, which is what we would expect, right? And then maybe you did the midpoint one too. Be curious to compare all those. All right, so those are the different kinds of approximations that we do. And the last thing I want to show you is sometimes we are given functions in the form of a table of data. All right, so in that case, we might have something like in other words, we don't have an f of x. We just have a table of data that might look like let's see. We've got 7. So let's say we had 0, 2, 5, 7, 10, 13, and 14. And then we had function values -3, 0, 2, 5, 5, 1, -2, something like that. So how do you deal with this? Well, we could do a couple different things here. We could find the right Riemann sum with, let's say, let's do all 6 with 6 rectangles. And if you're looking at that and say, wait a minute, there's 7 values there. Yeah, but the rectangles are defined by, they'd be 1, 2, 3, 4, 5, 6, right? So the right Riemann sum with 6 rectangles, if you're looking at this thinking that's a problem, it's not a problem. It just means we have kind of lopsided, lumpy looking rectangles, like in the very first example that I drew for you. So the first rectangle is 2 wide, and then the right endpoint, we use the right endpoint to define the height. In this case, that's 0. The next one is 3 wide, height of 2. The next one is 2 wide with a height of 5. 3 wide with a height of 5. 3 wide with a height of 1. And 1 wide with a height of -2. And I'll let you figure out, you can pause and figure out what that is. You can use your calculator, whatever. a midpoint sum with 3 rectangles. If we did 3 rectangles, then we would have 1, 2, 3. Like that, right? So now we have a midpoint, right? There's a point that's in the middle of each one of those. So the midpoint sum with 3 rectangles, the whole width of it's 5 wide, right? We still look at the whole width here, and its height would be 0. That's that midpoint. Plus, the whole width here is 5, and the midpoint value here is 5. And then the last one is 4 wide, and the midpoint here is 1. These are just approximations, so don't get stressed out now if it doesn't seem like this is right. And then lastly, we could do trapezoids. With 6 subdivisions. So we'll do all 6 trapezoids. So again, remember the area of a trapezoid is base over 2 times the sum of the heights. So I'm just going to set this one up for you, and you can figure out the details. So the first trapezoid, the base is 2 over 2 times the sum of the heights, -3 plus 0. Second trapezoid is 3 as the base over 2, always over 2, 0 plus 2, plus next one is 2 as the base, 2 plus 5. This is tedious, but it's not hard. 3 base of the next one, 5 plus 5, 3, the base of the next one, 5 plus 1, 1, the next one, and 1 plus -2. There you go. 1, 2, 3, 4, 5, 6 trapezoids. And those all give area approximations for this. What method we use kind of depends on the context. Sometimes we'll be asked to use a particular method, but that is a rundown of the different methods that we will use. Enjoy.